Yeah, so you could figure it out from the reduction potential chart, or you could try it one way. So copper's going to oxidize, silver's going to reduce. What's my cell potential? Or silver's going to oxidize, copper's going to reduce. What's my cell potential? And then you can figure out which one is more noble. However, I'll give you the chart on the exam. But that's good. That's a good way to tie together what that chart means and what these reduction potentials actually mean. And it's nice to try it both ways, because then you know when you have a negative E0 cell, that's thermodynamically unfavorable, and so you need to figure out what that means in the context of the problem. Yeah?
Could you explain how to calculate the potential between concentration cells?
Oh yeah, sure. That's a good one. Lots of people said you could do it on the homework, but then they didn't make any calculations, so I was hoping. But lots of people did a great job on that one. So it was like 50-50. Okay, so it was nickel 2 plus?
Yeah.
What number are we doing?
That's number 3 on homework 10.
Number 3. So let's do number 4 first. So say we have 1 molar Ni2 plus, 1 molar Ni2 plus, and we connect a voltmeter between these. What's the potential difference between these two cells? 0. Why? What's the formula that tells us that it's 0? Give me a mathematical relationship. So we could say that it's at equilibrium, so we know delta G equals 0, right? And so we know delta G is negative NF E0. N is always greater than 0, right? And so this is a good answer. It's at equilibrium. And so we have E0 equals 0, because delta G equals 0. We also have E equals E0 minus or plus? Minus RT NF ln Q. What's equation is this? Nernst equation. What's E0 for this cell? 0. We've got nickel on both sides, right? So there's no cell potential in this case, because it's the same reaction. Nickel's going to go to, or nickel 2 plus is going to go to nickel, or nickel's going to go to nickel 2 plus. Whoops. So this is 0. So what's Q?
That's going to be 1. So
Q is going to be 1 in this case, right? Because the reaction quotient, whether we take this as the product, or this is a reactant, or this is a reactant, and this is the product, no matter which way we make this ratio, it's going to be 1 over 1, or the same concentration over the same concentration, and ln of 1 is 0, and so this whole thing, E is going to be 0, because we're at equilibrium. So we have both the reaction, or both the equation of delta G, and we have the Nernst equation. Both of them are telling us that the concentration, or the potential is 0 when the concentration is equal. Okay, now given all that stuff, what were the concentrations in problem number 3? What's that? 0.78 and?
Maybe not.
Oh.
No, that's wrong. Yeah, it's zinc first off.
Oh, sorry. Okay.
And it's 1 and 3.75 times 10 to the negative 4.
Zinc 2 plus?
Yes.
Okay. What's N in this case? If you had to guess. N is 2, because we have 2 electrons that are going to reduce our zinc to zinc metal. What's Q? This is a little tricky. Q is just going to be one concentration over the other, and it doesn't, go ahead.
1 over 3.75 times 10 to the negative
1 over 3.75 times 10 to the negative 4. Okay, that's fine. What if I make Q is 3.75 times 10 to the negative 4 over 1? How does my answer change? What's the log of this, and what's the log of this? And how are they related?
Negatives.
Right? They're negatives of each other. So in one case, I'm going to get negative 0.1 volts. In the other case, I'm going to get 0.1 volts. Either of the answers are fine. It just matters which direction you hook your voltmeter up to. So the potential difference is 0.1 volts in each case. And we get that because this is 0. Let's see. So E equals negative RT over 2 times F ln of Q, and Q is either one of those. So anytime I ask about concentration or concentration differences, remember this Nernst equation part where you have to calculate the cell potential first. So using all the things that we've done with cell potential where you add up the reactions, etc. And then this ln Q, don't forget how to write a reaction quotient and put in the concentrations and then solve for the potential. So you had a few homework questions on Nernst equation. Does that cover number 3? Yeah. So the key for number 3 is it didn't matter which way you constructed Q. You just either got a negative answer or a positive answer, and both were acceptable. Did I see a hand? No? Other questions? Sorry, it's my phone chirping. Yes?
How can you determine if the battery is rechargeable or not?
How can you determine if a battery is rechargeable or not? So that's a difficult question to answer. Did I put that on the study guide? No.
Not sure.
What's that?
I'm not sure.
Yeah. So what's the essence of a rechargeable battery? I mean, why does it recharge? What do we do to it? That's right, we reverse the reaction, so that's a very good answer. So let's see if we take, I'm just going to do an easy one because I know it. Lithium right? So we have a standard potential of lithium carbon going to lithium ion plus an electron. Then we have lithium ion plus an electron going to lithium X cobalt oxide. So we can come up with the cell potential for this. And so when the cell potential is positive, do we get, and it's greater than 0, do we get energy from that, or do we have to put in energy to make the reaction happen?
Get energy.
We get energy, right? Because this tells us that the reaction is thermodynamically favorable. And so if we get an E0 cell, we add these up. If E0 cell is greater than 0, we know that the reaction is going to happen, right? In order to recharge it, we need to apply a potential that's greater than E0 cell to drive the reactions backward. And it really depends on the details of the reaction whether they'll go backward or not. We can always try and apply a potential that's higher than E0 cell. But whether the reaction's reverse or not depends on the particulars of the reaction. So we know lead-acid batteries are rechargeable, lithium-ion batteries are rechargeable, nickel metal hydride, but some things aren't rechargeable, and it just depends on the details of the chemistry. Yes?
When you say larger, do you mean larger but in the opposite sign?
That's right, larger but in the opposite sign. So when I say apply a potential versus the potential comes out, it is the opposite sign. Okay. Other questions? Make sure sure you pick up your homeworks. You got the benefit of getting them a day earlier than other folks. Happy to answer any more questions. Go ahead.
With respect to Fourier diagrams, what would we be asked to like find just the state of like, the cell at a specific?
That's right. So the phase, you know, if I give you the potential and pH, you could tell me what phase you're in. Or if I can say, perhaps you want to put aluminum into solution, what potential and pH would you use? Things that we covered in questions in class. But really being able to interpret what those x and y axes are and how to move around on them. Yeah.
So if you're applying a negative cell potential to a system, you're adding energy to it, right?
That's right. So if you're driving a reaction backwards, or you're applying a potential to something that has an E cell that's negative, you're going to move it in the opposite direction, right? Because you're going to take a thermodynamically unfavorable reaction and you're going to make it favorable by applying a potential. So say if E cell is negative 1.3 volts, this is thermodynamically unfavorable, right? It's not going to happen. So what you're going to do is you're going to apply a potential that's higher than that to move the total cell potential above zero. Then it becomes thermodynamically favorable, and then you drive the reaction the other way, right? Because say if you have A goes to A plus 1 electron, and our E0 cell is negative 1.3 volts, that tells us that it's unfavorable to go in this direction. But if we add energy or we add potential, we can drive it in the opposite direction by overcoming this thermodynamically unfavorable cell potential. And the easiest way to think about that is water splitting, right? So you say in one direction you can split water, in the other direction you get energy back from combining hydrogen and oxygen. So I always default to that one because that's easy to figure out. It's really easy to remember for me. Yeah?
There's an equation on here relating the overpotential to the current.
Ah, that's right.
System. Do we need to know the details of that?
No, so I